Welcome! In this video we will look back at what this week has brought us and look forward to the other parts of this course. And you have seen that the global transition to a low-carbon economy is not only a technological challenge, but also a systemic one. It requires the careful coordination of material and energy demands, supply chain capabilities and policy frameworks that enable sustainable innovation. And as the demand for renewable energy technology will grow, so does the need for critical materials, such as rare earth elements, high-grade steel, and advanced composites. These materials are essential for manufacturing solar panels, wind turbines, batteries, and we also saw the hydrogen infrastructure. However, their extraction and processing often come with environmental and also geopolitical risks. And to address this, supply chains must evolve from linear models to closed-loop systems that prioritize reuse, recycling, and resource efficiency. In the Circular Economy Feasibility Evaluation Framework that has been presented, we provide a roadmap for managing this transition. It emphasizes the importance of data visibility across the entire product lifecycle, from production and use to end of life and material recovery. And tools like digital product passports and semantic data platforms are crucial for tracking material flows, ensuring compliance and enabling reverse logistics. And this data-driven approach helps to align material supply with future demand. For instance, knowing when and where solar panels will be decommissioned allows for the timely recovery of valuable components, reducing the need for virgin materials extraction. And it also supports market transparency, enabling manufacturers and recyclers to plan investments and operations more effectively. Policy is a key enabler of circular supply chains. Regulations mandating extended producer responsibility, product traceability and recyclability standards create the legal and economic incentives that are needed to shift industry behavior. And without such frameworks, market forces alone may not drive the necessary investments in data infrastructure, recycling technologies, or sustainable design. The case of the Port of Rotterdam offered us a compelling example of how electrification and hydrogen integration are transforming industrial energy systems. And faced with the urgent need to decarbonize, the port is investing heavily in offshore wind energy, aiming to connect 7.4 gigawatts of capacity by 2030. And this renewable electricity will power large-scale electrolyzers which convert water into green hydrogen, and in that way a clean energy carrier for industry and mobility has been produced. The hydrogen infrastructure being developed at Rotterdam is extensive and material intensive. It includes pipelines, storage tanks, maritime terminals, and all of which must meet stringent safety and performance standards. Materials such as high-strength carbon steel, titanium, and composite resins are selected for their durability, corrosion resistance, and recyclability. Policy frameworks at the national and European levels, such as the European Hydrogen Strategy and the Fit for 55 package, play a central role in aligning infrastructure development and climate targets. And these policies will be introduced in more detail in the next weeks. The successful transition to circular and electrified energy systems depends on the triangular alignment of demand, supply, and policy. Demand for clean energy and materials must be met with reliable and sustainable supply chains, supported by robust data systems and forward-looking regulations. Only through this systemic integration, we can achieve a resilient, low-carbon future that is both economically viable and environmentally responsible.